أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم أنزل الله عليك الكتاب بالحكمة وعلمك ما لم تكن تعلم وكان فضل الله عليك عظيما. ये रसूलुल्लाह सल्लल्लाहु अलैहि वसल्लम को कहा जा रहा है कि अल्लाह ताला ने आपको किताब और हिकमत अता फरमाई और वो सिखलाया जो आपको नहीं जानते थे, और बहुत ज़बरदस्त फजल है अल्लाह ताला का. तो any kind of knowledge that is given is from Allah, and it is a great blessing of Allah. Now, today we are going to cover more of the univariate normal distribution theory, and as usual I am going to focus on the practical aspects. So you see, when a building is constructed, you have the engineering which is taught in NET in many years, and you have the architects, and then you have the people who are putting the bricks together, mazdoor. So I am more or less concerned with teaching the bricklaying, but in this lecture we are going to do a lot of engineering also, so a lot of theory and but I will point out the places where we learn about the real activity on the ground, which is the important part. So, our lecture today is about bivariate normal distributions. Basically, if you take the material from last lecture, which is on univariate, and this lecture, you could probably make a whole course out of this. So this is not, but it's basically because there's a lot of theory which, if you go on and explain things in detail, it can take a lot of time. I'm just going to go over the functional, how you operate the steering wheel and how you put on the brakes, and not worry about how it is built, which requires a lot of time. Okay, so we start with the basic definition. That there is a bivariate joint density function. So if you have any two random variables, they have a joint density function. This is a function which we can call f of xy. Sometimes I call it j of xy, just to show that this is a joint density. So the joint density function has these two properties. It has to be non-negative, and it has to integrate to 1. This is the same thing because the positivity is required for probabilities, and the total probability has to be 1. So it has to be, the whole integral has to be between 0 and 1. Now the probability that x and y belong to a region A. So this region A here is any region in xy plane. The outcomes are taking place on the Euclidean plane with the xy coordinates, and so any region can be an outcome. Will the random variable land inside this region? That is the question, and so the probability of that event is going to be obtained by integrating, taking the double integral over a of fxy dx dy. One thing important to note is that this function f can be greater than 1, even though the integral has to be less than 1, because the integral is obtained by integrating over a region. So for example, if you have a density which is in a small region, like if you have a random variable which takes values from between 0 and 1/2, with equal probability, uniform, then the density function will have the value 2 at all points, because the value of the function will be multiplied by the area of the region, so 2 times 1/2 will come out to 1. So the function itself can be very high. It's very useful to think of the density function as the infinitesimal probability. So this is something which is not taught in calculus, but basically it is very useful to understand infinitesimals, otherwise one gets very confused in probability, because basically you see one fundamental problem with continuous variables is consider a uniform random variable. A uniform random variable has outcomes in the range 0 and 1, and all values are equally likely. This is the intuitive idea. But if you look at what is the probability that x equals 1/2, well, it's the integral of the density function over that point. And what's that integral? Huh? No, just at 1/2, from 1/2 to 1/2. It's 0 because
upper and lower limit are same.
Huh?
Upper and lower limits are same.
Yeah, exactly. The probability at any point is 0 because you cannot integrate. You can integrate, but you just get the outcome 0 because there's no volume, there's no area in that region. So basically, the integral of a function is the area of the region over which you are integrating times the value of the function. But if the area of the region is 0, then there's no volume in it, so no matter what the value of the function, the outcome is going to be 0. So that means that every single outcome has probability 0, but one of these outcomes is going to take place because the whole space has probability 1. So this is a paradoxical situation. I have even written a paper about this, but the simple way to think about it is to say that there is a probability at that point which is f of x dx, where dx is an infinitesimal. Now what is an infinitesimal? Well, an infinitesimal is a number which is bigger than 0, but it is smaller than 1 over n for all n. So this is, or you can say, one way to simplify it is, infinitesimal is a number which is between 0.99999 repeating and 1. So these two are not exactly the same because there is this 0.0000 with infinite number of zeros, but then with a 1 at the end. So that's an infinitesimal. Now this can be in regular calculus. These things don't exist. Infinitesimals are not allowed to exist. But there is a way to do mathematics in which you can allow them to exist. And so here, in probability, it's convenient to think of the infinitesimals as existing because then we have some probability. It's a very, very small probability. It's smaller than 1 over n for any n, but still it is not 0. So we have f of x dx probability at every one point. Okay. So, and then when you integrate, you just add up all of these infinitesimal probabilities, and if you add up infinite numbers of infinitesimal probability, then you get something positive. Okay, so here's what a graph of a bivariate normal density looks like. It's symmetric and rises to peak at the origin and declines smoothly. And basically, what does this graph show? This is you see, it's a graph over the plane. The probability is in the plane. The probability in any region of the plane is the area under this graph. So that's how to intuitively think about that. Now, mathematically, when you have a bivariate normal distribution, this can be written in vector form as follows. You have two variables, x and y, and we can stack them one on top of the other to form a 2 by 1 vector. And I will call that z. And now this is a bivariate normal. Normal also has the mean mu and the covariance matrix sigma. The mean vector mu is again two component. One is mu sub x and the other is mu sub y. Mu sub x is actually the mean of x and mu sub y is the mean of y. And then there's this covariance matrix which has 4 entries: sigma squared x, sigma xy, sigma yx. You will see that sigma yx and sigma xy are the same, so these are just one entry, and then sigma squared y. So this bivariate normal distribution has 5 parameters: mu x, sigma squared x. These are the parameters for x. So we have already studied in last lecture the single univariate normal distribution. So x has mean mu x and variance sigma squared x. Y has mean mu y and variance sigma squared y. And there is one more parameter, sigma xy and sigma yx. These two are the same, so there are 5 parameters. So basically the bivariate normal distribution has one additional parameter, sigma xy, which is the covariance of x and y. So the two means and the variances are the things we already know from our study of the univariate normal distribution. So there is one additional parameter, the covariance, which we have to study in this lecture. What is the covariance, what it means, and how do we work with that? So the formal definition of the density is given here in this equation. F of xy is 1 over 2 pi sigma x sigma y times the square root of 1 minus rho squared times the exponent of something complicated, but we will analyze this later and see that it's not so complicated. So, but if you look at the terms, it's useful to see that it's x minus mu over sigma, that's the standardization of x squared, and then y minus mu over sigma, that's the standardization of y squared, minus 2 rho times the standardized x and the standardized y, so it's the product of the two, and then so that's enough to look at for the structure for now. Now we are going to look at the covariance and the properties, and so when we talk about covariance, first we have a general definition of the expected value for any function of two random variables, and it's just a standard generalization of the expectation in one dimension. So the expectation is the double integral of h of xy times the density integrated, that's all. So that's always the definition of expectation. Expectation of any function is the value of that function integrated against the density over the entire region of the density. One technical term which is useful is the support. The support is the set of all values of x and y at which the density is non-zero. So the support is the area where the variable actually has some infinitesimal probability as opposed to having zero probability. So if you have a positive random variable, then the support is only the positives and there is no support on the negatives. So that's just some terminology. Now the covariance function, this is the very important function, this is the heart of the bivariate normal density, is defined as the expected value of the product of x minus ex times y minus ey. So basically it says center the x, center the y, multiply them together and calculate the expectation. So the integral form is double integral of x minus ex, y minus ey, f of xy dx dy. Now one very important property of the covariance is that it is bilinear. It is linear in both variables separately. That you can establish using the properties of the integral if you analyze it a little bit, but I won't do that. Now one important consequence is that the covariance of ax plus b times cx plus d, first of all, the constants don't enter into the covariance, because you see, you take x minus ex, you center x, so if you add a constant to x, then that also gets added to the expectation. So when you subtract x minus ex, that will disappear. So the B and the D in covariance AX plus B, CX plus D doesn't matter. So covariance of AX plus B, CY plus D is the same as covariance of AX and CY. The B and the D drop out, and then you have the A and the C can come out. So covariance of AX CY is the same as A times C times the covariance of X and Y. That's part of the linearity. Now, one operation that you can perform, which gives us a different and alternative expression for the covariance, is here. This is just to show you how to operate with the covariance function. So we just take the expected value of this and we expand this. It's x minus ex times y minus ey. So we multiply it together and we get 4 terms. It's xy minus ex times y minus x times ey and plus ex ey. Now when we take the expectation of the 4 terms, I can split this up into 4 different expectations. The first term is the expected value of the product xy, and then all the 3 terms are the same because ex is a constant. So e of exy is just ex times ey, and all 3 terms are like this. 2 of them are minus, 1 of them is plus. So you end up with e times of xy minus ex times ey. So that's the other definition of the covariance. Now we will do some work on covariance later. Now we want to calculate in this lecture, this is one of the main objectives, 5 densities. We start with the joint density of x and y, and then we have 2 marginal densities and 2 conditional densities. So the marginal density of x is basically what is the density of x when x is considered all alone as a separate random variable instead of as a joint. So basically this involves just getting rid of the y, and you get rid of the y by integrating it out. So the marginal density of x is obtained by taking the joint density of xy and integrating with respect to y from minus infinity to plus infinity. Or alternatively, you can integrate over all y in the support of y. And when you do that, that will be the same because outside the support the density is 0. Similarly, if you want the marginal density of y, you have to integrate out the x. So now when you do this calculation, and you can do this, and it's a very nice and elegant calculation, and I used to spend a lot of time on that, and that's the engineering part, and you should learn how to do that. So you find that the marginal density of x is univariate normal with mean mu x and variance sigma squared x. You start with this one, which is the joint density, and you integrate. Oops, this is not. This is the joint density, and you integrate this, and you get the result. That x is normal with mean mu x and sigma squared x, and y is normal with mean mu y and sigma squared y. This is just a calculation. You take that joint density, and it's a little bit messy, but it's routine. It's not difficult. And I've given you materials in this separately which do all of these calculations. So that's one thing, that you integrate and you get the marginals. Now the more important thing and the more interesting thing is the conditional densities. So there are two conditionals. There is the conditional density of x given y. This is what is the density of x given that you know the value of y. Now actually there is not one conditional density. You have to understand that there are infinite numbers of conditional densities, because basically y, the random variable, is a pre-experimental concept. Post-experimentally, one outcome of y is observed, and then you ask, now that I know the value of y post-experimentally, what do I know about x? So this value of y, if the two variables have some dependence, and that's the general case, will give you some information about x. So the marginal density of x is what you know about x without knowing anything about y, and the conditional density of x given y is what do you know about x now that you know the value of y. So this is usually, these two things are different. And similarly the symmetric c of y given x. So now this is very easy to do, because the joint density is equal to the conditional density of x given y times the marginal density of y. This is a standard factorization. It's also equal to the conditional density of y given x times the marginal density of x. So these two are equivalent expressions. And now from this it's very easy to calculate, because it's just division. We know the marginal density, we just take the joint density and divide by the marginal density, and then there's again lots of messy algebra, but the result is very nice and elegant, that both of these densities, the conditional density of x given y and the conditional density of y given x, these are both normal densities, and you get there is a very nice way to express this result. Basically, if you standardize things, then the results are nice. If you don't standardize them, then the formulas look awkward and different, and you have difficulty understanding where they come from. But if you standardize them, then they are very easy, and from the standardized formulas you can get to the non-standardized very easily by simple algebra. So that's why I look at the standardized expression. Basically, if you remember that the x given y is a normal, then all we need is the expected value of x given y and the variance of x given y. Once we have the mean and the variance, then we know what the normal density is. So the expected value of standardized x given y is just rho times the standardization of y. So that's very simple. Rho is the correlation coefficient. The expected value of the standardization of x minus mu over sigma, will be 0 if y does not give any information, right? If y and x are independent, then the standardization because it's a standardization, will have expected value 0. So now the correlation coefficient rho tells us how much relationship there is between y and x, and basically it says you take the standardized y and multiply it by rho, and that's the expectation of the standardization of x. So it's very simple and easy to understand. When you translate this formula by algebra, then you get the expected value of x given y is equal to mu x plus rho times sigma x times y minus mu y over sigma y. So now this formula looks complicated and ugly and asymmetric, but if you look at the previous formula, you see that you get it by multiplying out. When you look at the expected value of standardization of x is equal to rho times the standardization of y, then you multiply both sides by sigma x, and then you add mu x to both sides, and you get the second formula. So it's very simple, and it follows immediately from the relationship between the standardizations. Here I have made what might be called a notational mistake, in that I have used capital Y on both sides. Actually, when you take the conditional expectation, you are talking about the observed value of y. The conditional expectation is defined for all observed values. So it has both meanings. It can be thought of as conditional expectation, condition on the random variable, in which case it's a function of the outcome of y, or it can be considered as a fixed particular variable for a particular y. So there's a little bit of a confusion. It works in both ways, but you have to keep in mind that there are two different interpretations of this. One is the interpretation of this post-experimentally, when there is an actual outcome of y which has been observed. It is true for that also. Or you can think of it pre-experimentally. It is also true for that. It has different meanings, the same formula. Now, that's the expected value. And what about the variance? Well, the variance is interesting. The variance of the standardization of x given y is 1 minus rho squared. This is very interesting, because basically if rho is 0, that's 0 correlation, then the variance of the standardization is 1. And that's what it should be, because standardization always has variance 1. But now basically if there is correlation, then y will give you some information. The information will reduce the variance. That's to be expected, because now there is some fluctuation in x, but this fluctuation will be reduced when you have some information about x, and y is giving you some information. So basically it's reduced by rho squared. If rho squared is 1, which is perfect correlation, then the variance is 0. In that case, the value of y completely determines what x is. And if rho is 0, then the variance is unchanged. It's the same as the marginal. And in the middle, it varies linearly with rho squared. So it's a very sensible and simple and easy to understand formula. So from this, again, if we multiply by sigma squared, the variance of 1 over sigma x times x, you can factor out 1 over sigma squared here, because variance of a constant times x is the square of that constant times the variance of x. So the sigma squared comes out with the constant, and you can put it on the other side. Subtracting mean mu x doesn't have any effect on the variance. So basically variance of x given y is 1 minus rho squared times the sigma squared x. So these are the conditional mean and variance of x. And from this, we can get the formula. What is the conditional distribution of x given y? Well, it's normal, with mean equal to the expected value of x given y and variance equal to the variance of x given y. And so it's the formula here. Formula is a little bit messy, and if we put it down like this, it will be very hard to understand. It's normal mean mu x plus rho times sigma x times the standardization of y minus mu y over sigma y, and that's the mean of x given y, and the variance is 1 minus rho squared sigma squared x. So that's the conditional distribution. Similarly, by just interchanging x and y, you can get the conditional distribution of y given x. It's completely symmetric, so there is no change, exactly the same meaning and derivation. And now, one thing that we note, that if rho equals 0, then the conditional distribution of x given y is the same as the marginal. The marginal is mu x and sigma squared x, and if rho is 0, then that's what it reduces to. And that's very important to understand, because basically rho equals 0 means that the x and y are independent. The knowledge of y doesn't give us any information about x. The marginal distribution of x, what you know about x without having any knowledge of y, is the same as what you know about x having knowledge of y. Now, rho will be, I'm running a little bit ahead in this lecture. Rho is 0 means that the covariance of x and y is 0. I'll prove that later. And if that is so, basically covariance xy equals 0 implies that x and y are independent. Now this is a very deceptive result, and people are very confused by this all the time, and it seems very likely that this confusion will persist, because this is a very special result. It only holds when x and y have joint bivariate normal density. In general, it is not true that covariance 0 implies independence, but for bivariate normals, it implies independence. In fact, what independence means is that the expected value of x to the m, y to the n is equal to the product of the mth moment of x and the nth moment of y is equal to the product of the separate moments for all integers m and n. This is a very strong requirement expected value of xy equals ex, ey. That's just one of these infinitely many conditions. But in the normal condition case, if just one of them holds, then all of them hold. But in general, independence means that this condition holds for all integers m and n, and so you cannot conclude from any one of them holding that all of them will hold. So independence is a much stronger condition than covariance 0. But in the joint normal case, the two are the same. Okay, so now we do some more description of the normal density. So one very important special case of the normal density is the standardized case, where both x and y are standardized. So here I define z of x to be the standardization of x minus ex over the standard error of x, that will be x minus mu x over sigma x, and let z of y be the standardization of y, so y minus mu y over sigma y. Then what is the density of z of x and z of y, the joint density? And that function is given over here, and it is a much simpler function now. It's 1 over 2 pi. The sigma x, sigma y have disappeared, but there is a square root of 1 minus rho squared, and then there is exponent of minus z squared x, z squared y, minus 2 rho z x, z y, 2 times 1 minus rho squared in the denominator. So this is the joint bivariate normal density for standardized variables. This form is. So again, if you start with this density, you can integrate out zx to get the marginal of y, integrate out y to get the marginal of x, and also calculate the two conditional densities. And here they have much easier form. And so these are the forms. Zfx, zy are both normal 0, 1 because we have standardized them. The conditional density is interesting. It's zx given zy is rho times zy. This is exactly what I said earlier. And the variance is just 1 minus, conditional variance is 1 minus rho squared. So if you look at the conditional distribution of zx given zy, the standardization of x conditional on the standardization of y, you get normal. The mean is just rho times the z of y, the standardization of y, and the variance is 1 minus rho squared.
1 minus rho square और इसके साथ स्टैंडर्डाइज करने की वजह से हमारे पास जो इसके साथ सिग्मा मल्टीप्लाई.
हाँ बिल्कुल. After standardization, all the sigmas disappear and all the mu's disappear. And one very important feature of the normal distribution is what you would call homoscedasticity, because in general in the conditional distribution the mean will also be a function of what you're conditioning on, the value of y, and the variance will also be a function of the value of y. But in the normal distribution it has a very special property that the variance does not depend on the value of y. So this is a very special property of the bivariate normal distribution. In general, this will not be true for general joint distributions. Both mean and variance will be affected by the conditioning. But in the normal distribution, the mean is affected by the conditioning, but the variance is not affected by the conditioning. The variance is affected by the conditioning, it becomes smaller, but it doesn't depend on the actual value of the y which is observed. And again, we have independence between the two if and only if rho equals 0. When rho equals 0, then the mean becomes 0 and the variance becomes 1. So the conditional is the same as the marginal. So now what we are going to do is basically you know something if you know how to build it. This is the concept. So now we start with the two. We know what an independent standard. We know what a standard normal 0, 1 is. What do we know? Well, we know what it is by generating it, by generating on the computer. So when we generate these numbers on the computer which are normal, then we know that this is what a normal random variable is. So if I can generate one random variable which is normal 0, 1, I can also generate a second which is independent normal 0, 1. So I want to start with these and show you how to get to the standard bivariate normal. So first, when we have independent standard normal densities, then the joint density is 1 over 2 pi x 1/2 x squared plus y squared, because the joint density is just the product of the two marginals, because these are independent. So for independent random variables x and y, the joint density is the product of their separate densities. So this is a bivariate normal, and the vector of means is 0, and the covariance matrix is identity. That we want to explain. What is the covariance matrix? So the covariance matrix consists of these 4 entries. One is the variance of x, the other is the variance of y, and the off-diagonal term is the covariance of xy, which is the same as the covariance of yx. Now, one very important property of this covariance matrix is that its determinant is always greater than or equal to 0, typically greater than 0, which means that the covariance of xy squared and covariance of xy and covariance of yx is the same. You can easily see from the formula, because it's the product, and the expected value of xy is the same as expected value of yx. So this is going to be the same. So the covariance of xy squared, which is the minus term in the determinant, has to be less than or equal to the variance of x times the variance of y. This is called the Cauchy-Schwarz inequality, and it has its own proof, but I won't bother with that. But basically what it means is the covariance matrix is always has a positive determinant. In fact, it has to be a positive definite matrix.
So it is possible a variable has 0 variance?
Yes, a variable has 0 variance if and only if it's not really random. So that means that it equals its mean with probability 1. So it's just a constant. So you can regard it as not random because there is no random fluctuation. But it's useful to have that as a limit for as the variance goes to 0, the random variable converges to a constant. So it's just a notational issue that do we call that variable random or not. It's just as convenient. It doesn't really matter. But the thing to understand is that when the variance is 0, then there's no randomness left in that. Okay, so now some more properties of the covariance. One formula for the covariance is EXY minus EX times EY. And now this has to be 0 for independent variables, because the expected value of a product is the product of expected values for all independent variables. And this is true. So covariance always 0 whenever x and y are independent, and this doesn't depend on normality. The converse is true only for normals. That is, covariance 0 implies independence for joint bivariate normals only. Now, one important aspect of the covariance formula is that what is the covariance of x with itself? Well, if you just look at the formula, covariance xx, it's ex squared minus the square of the expected value, which is just the variance of x. So, and that's greater than 0 for every random variable if it's random. Otherwise, it can also be 0 if it's not random. So, the covariance of x is just the same as the variance of x. If x and y are independent, then the covariance is 0. Now, the correlation between x and y is just the covariance, by definition, it's the covariance of the standardization of x with the standardization of y. So, standardization of x is, as usual, x minus ex over standard error of x, and standardization of y is y minus ey over standard error of y. So from these formulas you can also see that the correlation is the covariance of xy divided by the standard error of x times the standard error of y. Put the product of the standard errors in the denominator. Now, some more properties of the covariance. Basically, covariance is what differentiates between the bivariate case and the univariate case. So now what we are trying to do here is to develop the formulas that I start with two independent normals. How can I convert them into two dependent normals? Because that's the general case that I want to. So I'm trying to show you, between all of these formulas, there's lots of theory and lots of formulas and lots of integrals. But for the bricklayer, the one who is the mazdoor, he needs to know, how do I build this variable? And that's what we're trying to do. So between the huge number of 99 pages of work, and then there's this one page of how do you put the brick on. So this is this. So covariance of xy is the same as covariance for x plus a, y plus b. Adding constants doesn't affect. So covariance of xy is the same as covariance x minus ex, y minus ey. So it means that we only need to think about the centered variables when calculating the covariance. Now, take xy to be independent standard normals. We're starting with these independent standard normals and we want to construct correlated variables with correlation rho. If I know how to do that, then I know how to put the brick down. So, choose constants a and b such that a squared plus b squared equals 1. And define this new random variable z, which is equal to ax plus by, and x and y are independent standard normals. Then what's the variance of z? Well, x and y are independent, so variance of z is the sum of the variances. So it's variance of ax plus variance of by is equal to a squared times the variance of x plus b squared times the variance of y is equal to a squared plus b squared, because x and y are a standard, and so that's 1. So z has variance 1. Now what about the covariance between x and z? Well, that's equal to covariance for x and ax plus by. Now covariance is linear, so you can split it up into two terms. It's covariance of x with ax plus the covariance of x with by. Now the linearity means that the a and the b can come out. So you have a times the covariance of xx, which is just the variance of x, and b times the covariance of xy, which is 0, because x and y are independent. So this is just a. What that means is that x and z have covariance a. So now I have two variables, x and z. These are both standard normal separately. Z has mean 0 and variance 1. And x has mean 0, variance 1. And the correlation of x and z is a, which is what. So now I have constructed two standard normals which have marginal n01, and they are correlated with rho correlation. So I know how to go from two independent standard normals to two correlated standard normals. So this is for the bricklayers. If I start with to put it together, xy independent standard normal, define zx equals x. This would be the standardization of x, but x is already standardized, so I don't need to do anything to it. And zy defined as rho x plus by, where b is the square root of 1 minus rho squared. Now then Zx and Zy are both normal 0, 1. Zx is of course x, so it is normal 0, 1. Zy ke liye, if you take the expected value of Zy, that will be rho times the expected value of x plus b times the expected value of y. Both y and x have mean 0, so the expected value of z will have to be 0. And now if you take the variance of zy, that will be rho squared times the variance of x plus b squared times the variance of y. And if you calculate that, you will find that that's equal to 1. So the variance of zy is 1 by construction. The mean is 0 by construction. And now the correlation between zx and zy is rho. That's why we constructed z. Basically, I constructed z by x and y are independent. I took y and subtracted a little bit from it and added some portion of x to it in order to create correlation. So some portion of x was added into the y, and that created the correlation, because now this z variable has a little bit of x and a little bit of y. So the part which is x is correlated with the x perfectly, and the part which is not is independent. So basically by adding those two, I get a partly correlated variable. And now how much weight I put on the two will change the correlation from 0 to 1. If I put all the weight on y, there will be 0 correlation. If I put all the weight on x, there will be perfect correlation. And in between, I get all in between correlations. So the joint density of Zy is exactly as before. It is the standardized correlated density, which we have already seen the formula for. So I've just duplicated it here. Now this gives us two variables which are correlated and with rho, and they have mean 0 and variance 1. Now suppose I want mean x and covariance sigma squared x. That's very easy. The correlation is not going to change when I make a linear transformation on x and then I make a linear transformation on y. So I can just adjust them to have whatever mean I like and whatever variance I like. Correlation will remain fixed in this operation because the correlation is the covariance of the standardized variable. So if I destandardize them, it won't make any difference to the correlation. So I define S equals to mu S plus sigma S times Zx, and T equals to mu T plus sigma T times Zy. And now I have S and T are bivariate joint normal with correlation equal to rho, covariance equal to rho times sigma S times sigma T, and they have the marginals that I want, mu S and sigma squared S, and mu T times sigma squared T. So this is again the building function. So now I can build any kind of bivariate normal density that I want by starting from independent standard normals. First, I take the independent standard normal xy, and then I create standard normals which have correlation rho. Then I adjust the mean of the first one to whatever I like, sigma, and the standard deviation to whatever I like, because I add the mean to get the mean I want from 0, and I multiply by the sigma to get the standard deviation I want. And I do this to both variables separately, and this does not disturb the correlation between them. And now I have a general bivariate normal, any mean, any variance for the first variable, any mean, any variance for the second variable, and any rho that I like for the correlation between the two. So all 5 of the parameters are completely under my control. You tell me the 5 parameters, and I know how to build my 2 independent normals, and I can, from my 2 independent normals, I can construct a bivariate normal according to all 5 parameters that you specify. So I know the perfect construction work. This is really the most important thing, and unfortunately, when you this is one thing which is never taught. I mean, if you can go through books and books and books, and you will not understand that this is what is how you do, because in engineering school they don't teach you how to go and build houses, they teach you the theory. So this is for the bricklayers. There are 2 steps required to get from IID normals to general. First you induce the correlation, and then you adjust the mean and the variance of the both variables. Okay, the reverse process is also important. When you have a house, how do you deconstruct it, take it apart? So basically, starting from the general bivariate normal, I want to go back to the two independent standard normals. So we know how to standardize for one univariate normal, which means subtracting the mean and dividing by the standard error. But now how do I standardize from a general bivariate normal process? So now I have 5 parameters. So again, this is a two-step process. First, you standardize x and y separately. So you define v equals to x minus ex divided by the standard error, and w equal to y minus ey over the standard error. And now vw will be standardized normals, but they will have correlation rho. So vw are standard normals, normal 0, 1. Covariance of vw is equal to rho, which is the same as the correlation of x and y, because the correlation is the covariance of the standardized variables. That's the definition of correlation. Now, I want to go from VW to independent normals, ZV and ZW. These are going to be transformations of linear transformations of VW, which are independent. So I want basically to undo the dependence. So take one of the variables to be V. You can take it to be W also, it's the same. But you have to do one or the other, you can't do both. So I take ZV equal to V, and now I take ZW to be W minus rho V. So basically I am extracting, I know the structure. This is the important thing to understand individually. What W is correlated with V because it has one part which is actually exactly the same as V, but a little bit scaled, and it has one part which is independent of V. So if I take out the part which is dependent on V, what I will be left with will be independent of V. So now I take W and subtract from it rho V. Exactly, rho is the correlation. So rho V is exactly the part of W which is coming from V. So when I take W minus rho V, this part is going to be independent of V. That's very important. So now I have defined these two variables. I take the covariance of ZV and ZW. So by applying the linearity property of covariance, covariance of VW is, so this is covariance of V with covariance of W minus rho V, and that splits up into two terms. It's covariance of VW minus rho times covariance of WW. Right? No. Sorry. Yeah, it's rho times the covariance of VV. That's I got this wrong here. But it doesn't matter. So it's going to be the first covariance of VW is rho, because these are standardized, and the covariance of VV is 1. So this will become rho minus rho, which will be equal to 0. And now the magic of the normal distribution is that if the covariance is 0, then the two V and ZV and ZW are independent. So basically now ZV is normal 0, 1, ZW is also normal 0, 1, and these are independent. For the normal 0, 1, I haven't actually proven that. You have to look at the expected value of ZW, and that will be 0 by linearity. And then you have to look at the variance of ZW. Oops, I made a mistake here. Yeah, I think you have to have ZW equal to the square root of 1 minus rho squared times W minus rho V, and then you get normal 0, 1. Otherwise, the variance of ZW, as I have written, will be 1 plus rho squared, which is not going to be standard normal. So I made a mistake here. So after you do that, so basically now I've shown you how you start from standard normals, a general bivariate normal density, and you make a sequence of steps to reduce it to independent standard normals. This is a very common technique in working with general normal distributions. It's very hard to handle the standard general normal distribution multivariate case. We are looking at in the bivariate because it's easier to understand. In the multivariate case, we will do the same things, but it will be more complex. So basically what you do is you make a linear transformation and you get to your standard normal, which has mean 0 and variance 1, or covariance matrix identity. Now the calculations are very easy for the standard normal. All the calculations are very easy for standard normals. So you do all of the calculations and then you undo. So because of linearity, you can usually do this. And in the first step, you start with general normal, you reduce it to standard normal by a linear transformation. Then you do all your calculations that you need to do, and then you undo the linear transformation to get back to your original framework and you get the original result. This is a very common process. And okay, now there's one more very important way to generate. I'm going to basically, this whole lecture is about how you construct general bivariate normal. So I've shown you one way. This one way that I've shown you is based on the joint density. Now I'm going to show you how to generate normals based on the conditional density. So we start with pre-experimental. So again, our goal is the same. I'm going to generate a general bivariate normal from my basic bricks, which are normal 0, 1s. So now an independent normal 0, 1s. So I have one independent normal 0, 1, y, which is normal 0, 1. I know how to generate that on my computer. So I generate this and I get one actual value. So I have an observed value of y, 1.2. Now I know from the calculations that we have done earlier, then the conditional density of x given y equals to little y. So now I'm looking at the observed value of y is normal with mean equal to rho y and the variance equal to the square root of 1 minus rho squared. This is in the general bivariate normal with correlation rho. So now I can generate a z which is normal 0, 1, which is independent of y. So I start with that. Now I want to change the mean to rho y. So I just add rho y, and I want to change the variance to 1 minus rho squared. So I multiply the z by square root of 1 minus rho squared, and that's it. So if I set x equals to rho y plus the square root of 1 minus rho squared times z, then x will have the conditional distribution, normal with mean rho y, and variance. Again, there's a mistake in here. The variance is not the square root of 1 minus rho squared. The variance is 1 minus rho squared itself. The standard error is the square root of 1 minus rho squared. So now we have, that's it. This is it. X given y has this distribution. Now the marginal distribution of x will be normal with mean 0 and variance 1. And the covariance between x and y and the correlation between x and y will be rho. So
pre-experimental y standardized हमारे पास है 0, उसका mean और variance 1. हमने यहाँ पे assume किया है कि x condition हो रहा है y is equal to y. Post के बराबर किया हुआ है pre को. ये assumption है हमारी यहाँ पे. First one.
नहीं. Basically, I am now generating actual values, observations of x and y, which are normal, just like you generate numbers. So after having generated 1.2 and I know the value of rho, then I multiply, so suppose rho is 1.5, so I have 1.2 is the observed value of y, so I want an x which has mean equal to 0.6, which is half of the observed value, and the variance I should be 1 minus 0.5 squared, the variance should be 0.75. So now I want a normal with mean 0.5 and variance 0.75. I have an independent normal 0, 1, which I generate on the computer, which may be minus 3. Minus 3 is too large, minus 1.7. then so my formula tells me that take this minus 1.7, multiply it by the square root of 0.75 and add 0.5, and you will get a number, and that number will be your x, which has the desired density, conditional on y. And now the marginal density of this x is normal 0, 1. This is what we know from theory. This is where the engineering comes in. This is what the bricklayer doesn't know. That, okay, I'll tell him, okay, this is the recipe for your generating, but why did it come? He will be completely lost. He will never be able to understand. So that's all of that mathematics which shows why, given this conditional density and that marginal, the marginal of x will be normal 0, 1. There's a lot of heavy duty mathematics which goes into proving this. But doing it is very easy. It's just a recipe. So both are normal 0, 1. They have covariance correlation of rho. And now I want to get the general bivariate. These x and y, these are both normal 0, 1, and they have correlation rho. General is very easy. You just change the mean to whatever you like and change the standard deviation to whatever you like by, if you take s equals a plus bx and t equals c plus dy, the correlation between s and t will still be rho. The mean of s will be now a because you've added a, and the mean of t will be c, and the standard error of s will be b, and the standard error of t will be c. So you can set the mean and the variance of s, set the mean and the variance of t, and the correlation is fixed at rho, and that's it. So now you have generated bivariate normal from two independent normals. Okay, so now we were going to look at some properties of IID bivariate normal random variables. So one of them is spherical symmetry. The joint density you can write, you see, you are multiplying two univariate normal densities. Each one has a 1 over square root of 2 pi. So the joint density will have 1 over 2 pi. The two square roots multiply and get 2 pi. In general, in the n-dimensional case, the factor that you have is 1 over 2 pi to the n over 2. Where n is the dimensionality of the normal distribution. So here in the case of 2 dimensions, it's 2 over 2 and it becomes 1. In 1 dimension, it's 1 over 2, it's square root of 2 pi, and so on. And in the exponent, I have e to the, I've forgotten a minus sign here. It's e to the minus 1/2 x squared plus y squared, e to the minus 1/2 x squared times e to the minus 1/2 y squared. So one important thing to note about this is that the density is a function of the distance from the origin. We are talking about the real plane, the Euclidean plane. X squared plus y squared is the square of the distance from the origin. And so basically the density declines, because it's minus 1/2. Technically is maximum at 0, and at 0 it's equal to 1 over 2 pi. And then because e to the minus x keeps declining with r, so the distance from the origin, so basically it keeps going down, and it goes down to 0 very fast because e to the minus 1/2 r squared is a very rapidly declining function, and that's why the normal density doesn't have outliers, because the function declines to 0 very rapidly, so there's not much probability left after you go out a little bit far away from the origin. And other densities, like the Cauchy density, you have something like 1 over 1 plus r, or something like r squared, and or r cubed. So those densities decline much slower, and in those densities you get much more, you have much better chance of finding something which is far from the origin. Okay, now we get to some more technical stuff, which is the spherical symmetry. This is very important to understand about the standard normal distribution. The standard normal distribution is spherically symmetric. It means that all directions are the same. And to understand this technically, it's useful to do a little bit of mathematics. and that mathematics is to convert the normal, bivariate normal, to the polar form. So conversion to polar form is done here. Now it's useful to think of the infinitesimal density as f of xy dx dy. And now I'm going to transform the xy. Remember, xy are your coordinates in your Euclidean plane. Now if you make a little triangle from the origin to xy, then you see that the distance from the 0, 0 to xy is r squared, which is x squared plus y squared. And if you look at the angle theta, which is made between the line, the triangle at xy and the x-axis, and call that theta, then you see that the vertical part, which is y, is just equal to r sine theta, and the horizontal part is x, which is r cosine theta. Now I want to get the density of the r and theta, the polar coordinates of the normal, because this has a very important meaning and very important use and very important to understand. So basically dx dy, this is just a formula for change of variables. Dx dy, the infinitesimals, is equal to j times dr d theta, where j is the Jacobian. The Jacobian is the determinant matrix, and if you just do a simple division, you can see that j is equal to dx dy divided by dr d theta, and that's exactly what it is. J is the determinant of this matrix of derivatives, dx dy dr d theta. So you take x and you divide it by r and theta, so you have partial x with respect to r, partial x with respect to theta, and you take the y and multiply, divide it by, differentiate with r and theta, and so you get this 2 by 2 determinant. And if you just look at x equals r cosine theta and x equals r sine theta, you can do the differentiations. So partial x with respect to r is going to be just cosine theta, partial x with respect to theta is minus r sine theta, because cosine differentiates to minus sine, and partial y with respect to r is just sine theta, and partial y with respect to theta is r cosine theta. And when you take the determinant, it's cosine squared minus r sine squared, plus r sine squared, so you just get r. So the crucial formula here is that dx dy is equal to r dr d theta. Okay, so from that we get the following change of variables. If you have fxy dx dy, that's 1 over 2 pi x, again I've forgotten the minus sign, minus 1/2 x squared plus y squared dx dy. Now we make the change of variables, x equals r cosine theta, y equals r sine theta. This implies that r is equal to the square root of x squared plus y squared, and theta is equal to the arctan of y over x. This is just inverting the two formulas. And then you get fr theta just by substitution is equal to r x minus r squared over 2 dr times 1 over 2 pi d theta. And these are the two densities of theta and r. The first density, the density of r, is r times e to the minus r squared over 2, and this ranges from 0 to infinity. The support is only on the positive side. And theta itself ranges from 0 to 2 pi, and the density is just 1 over 2 pi, which means it's a uniform density. It's equally likely to be anywhere. Now, क्या हुआ? क्या हुआ? So now, at this point, some people might be just completely mind-boggled. Lost, yes. I remember that in one of my lectures I said, "Oh, this course is completely beyond me. It's not for me." So this is the engineering part, and but not to worry. I mean, these things are not that difficult, and it's not important to know them. It's, what is important to know is the result of this, which we will show you. I'm teaching you how the bricklaying part, which is the important, how to put one brick on top of the other. So basically what we understand from this is that, okay, we'll go into that one. Okay, so the distance from the origin, you take a normal distribution, you generate xy, it's a point in the plane. Now, how far is that point going to be? Well, the square of the distance is going to be x squared plus y squared. Now, one very important property of the normal is that the sum of the squares of independent normal is a chi-square distribution. So x squared plus y squared is chi-squared with 2 degrees of freedom. So basically the square of the distance from the origin is chi-squared with 2 degrees of freedom, and this property generalizes to n dimensions. When you have n random variables and you take the sum of the squares, you have chi-squared with n degrees of freedom. So I know how far my normal is from the origin. This is the key, and how you derive that, that's part of the formula, but it doesn't really matter. All you need to know is that the distance is chi-squared n in n dimensions, the square of the distance. What about the angle? So there are two things which determine where this normal is. Now the important thing, the beautiful thing about the normal is that the angle is equally likely to be anywhere. So if you have a circle, choose any point on that circle such that all points are equally likely, and choose the r, the distance, according to the chi-squared distribution, and you have a normal distribution. So this is another way to think about the normal distribution. The distance is by chi-squared and the theta is uniform. So that's a very important insight into the structure of the multivariate normal distribution. Now there is one, so I'm going to use this insight to construct random variables. I've given you two ways to construct the general bivariate normal, and now I'm going to create a third way, and this third way is also important. This third way is based on the spherical symmetry, and is based on the fact that r is chi-squared 2. So now I want to show how to get from a uniform variable to a chi-squared 2. Now chi-squared 2 happens to have a very nice property. It has a very nice integral, unlike the normal, which has a very bad integral, it's impossible to integrate. So, but chi-squared 2 is easy to integrate, and it leads to a very simple formula. But first let me explain the so-called probability integral transformation.
लास्ट स्लाइड अगर हम देखें उसमें लास्ट स्लाइड में सम ऑफ एक्स स्क्वायर्स जो है वो r की इक्वल आ रहा है, ये डिस्टेंस है फ्रॉम ओरिजिन.
यस,
ये 1 से इंक्रीज भी हो सकता है.
क्या मतलब?
मतलब इसकी वैल्यू 1 से बड़ी भी हो सकती है.
ऑफ कोर्स.
और थीटा कैन टेक एनी वैल्यू.
Theta is just the angle, so it can, in 2 dimensions, it takes values from 0 to 2 pi measured in radians, and in n dimensions, the angle is determined is just a sphere, is a point on the sphere, on the unit sphere. That's called the angle. Angle can also be parameter.
यहाँ पर सर अगर r की वैल्यू 1 से इंक्रीज होगी फिर वो यूनिटी वाला कांसेप्ट डिस्टर्ब नहीं हो जाता?
You see, r can be anything. R can be 0 or close to 0, or it can be 50, or it can be 100. This is the chi-squared.
स्टैंडर्ड नॉर्मल की जो बात करते हैं वो उसमें डिस्टेंस फ्रॉम.
But the standard normal is mean 0 and variance 1. It can take any value between 0 and 3. Yani more than 3 is unlikely, but it can take any value between 0 and 6. 1 in trillion possibility. So 1 ki kya, yani 1 has no special standing in the normal distribution. When you have x squared plus y squared, then x squared can be, x squared can be can be 2, and x can be 2 and y can be 2. So these are values which are possible for normal, and x squared will be 4 and y squared will be 4, so r squared will be 8, so r will be the square root of 8.
मेरे माइंड में ये बात आ रही थी कि हम जितने भी फंडामेंटल लॉज पढ़ते हैं ना वो डिफाइन करवाए जाते हैं यूनिट सर्कल पर. मतलब उनकी
theta is confined to the unit circle, but r is not.
r can take any value.
R can take any value. Just like the normal bivariate normal, can take any value number, can be any point on the plane. It's just a different coordinate system, the polar coordinates. It's just you take the angle and you take the distance. That's, you see, one way to describe a point xy is to look at the rectangular coordinates x and y. The other way is to say what is the angle that is this point makes and what is the distance. These two pieces of information are the same. R and theta tell you where the point is, x and y tell you where the point is. That's all. And there is no the random variable, the normal variable does not take a value on the unit circle. It takes values everywhere on the plane. So r and theta can be any possible values. So now I want to explain how you generate random variables using this characterization of the normal density. So the CDF is, for any random variable, is defined to be f of x, which is probability x less than or equal to x, and the CDF always takes values between 0 and 1. It is a probability. So now consider a uniform random variable, and the uniform random variable between 0 and 1. So the probability that capital U is less than or equal to U is equal to U for 0 less than or equal to U less than or equal to 1. The probability of being less than 1 is 100%, probability of being less than 0 is 0%, probability of being less than half is 50%, and so on. This is a standard uniform variable. So if I take the capital F of x, which is the probability that x is less than or equal to x, and I ask what is the probability that U is less than or equal to f of x, that's equal to f of x automatically, because probability U less than anything is that thing. So that makes it possible to consider the variable x, which is equal to f inverse of U, where f is the CDF. The inverse function is, we will show how to calculate that. If x equals f inverse of U, that means that U is equal to f of x. So take any random variable x such that U equals f of x. So this is taking a random variable x and applying its own distribution function to transform that random variable. It's a way to actually smooth that random variable. So it's just a mechanical calculation. If you look at the probability that x is less than or equal to x, then x is by definition f inverse of U. So that's probability that f inverse of U is less than or equal to x. Now apply f inverse on both sides and you get probability that U is less than or equal to f of x, which is equal to f of x. So it's a little bit magical, tricky, nothing complicated in this, but still it seems puzzling. So anyway, the result of this is that if you take any random variable x and transform it by its own CDF, you get a uniform random variable. Conversely, if you take a CDF and apply the inverse of it to a uniform random variable, you get the random variable with the desired distribution. This is called the probability integral transform, and it's very, very common way to generate any random variable, because we know how to generate uniform random variables, but how do you generate a normal random variable? It's not, there's no direct easy method, or chi-squared, or gamma variable, or exponential. There are thousands of different densities. Now the Excel gives us rand, which is uniform between 0 and 1, and now the probability integral transform says the following: take any random variable, calculate its CDF, calculate the inverse of that CDF, apply that to the uniform, and you've got your random variable. Very simple. So again, the bricklayer part is very easy. This is what you do, and how you prove it, that's actually also quite easy, but it becomes mysterious. So x equals f inverse of U has CDF f. This is the probability integral transform. Take any CDF f, calculate its inverse, apply it to the uniform variable, and you've got the variable that you want. Very simple. Now, so what are the consequences of this probability integral transformation? Remember, Excel has a built-in function called norm S inverse, which is the inverse of the CDF of the normal. And what it does is, if you give it a probability, it calculates the x at which the normal distribution CDF reaches that probability. So now what our probability integral transformation says is that if you take rand brackets, which is uniform 0, 1, and apply norm S inverse to it, you will get a normal random variable, which standard normal random variable. So this is a very convenient way to generate a normal random variable in Excel, because when we want to, the other way that you already know is that you go into the data analysis and you ask it to generate, but those random variables that you generate, they are fixed, they are not recomputed. Sometimes you want, for simulations, that every time you run it, you get new random variables. So if you generate your random variables like this, then every time you do anything to the spreadsheet, they will all be recomputed. So you can do your simulations with your normal variables, which are dynamic instead of static. But this is actually special to Excel, because Excel has the built-in inverse normal. By the way, inverse normal is not a function which you can write down. There is no formula for it. It's just numerically computed. So this is not elegant, and this was not possible in the earlier days of computation. We couldn't use this method because we didn't have any formula for norm S inverse. And still you don't have in many computer packages you want. If this is not built in, then you can't use it. So the other way is the one that is based on the chi-squared, and that is the following. Okay, so now we are going to do again a little bit of integration. So the density function for the chi-squared with 2 degrees of freedom is, by definition, integral from 0 to x r e to the minus r squared over 2 dr. That was the density of the chi-squared 2. And this is a perfect integral in the sense that minus e to the minus 1/2 r squared, the derivative of that is r minus 1 e to the minus 1/2 r squared. So basically the standard calculus, this is called the fundamental theorem of calculus, that if the derivative of f is f prime, then the integral of f prime is f. These two are inverse functions. So since the derivative of minus e to the minus 1/2 r squared is r e to the minus 1/2 r squared, so the integral of that is the antiderivative. So we evaluate this at the two limits 0 and x. At the top limit x, it's e to the minus 1/2 x squared. At the bottom limit 0, it's just 1. There is a minus sign, so this can be written as 1 minus e to the minus x squared over 2. So that's f of x. So I want to calculate the inverse of that. Well, that's very easy. I set u equal to 1 minus e to the minus 1/2 x squared, and now I solve this function for x. That's how you get the inverse function. So it's just simple algebra. I pull the e to the other side, it becomes 1 minus u. Then I take the log, so it becomes log 1 minus u, and I have minus 1/2 x squared left. So then I multiply both sides by minus 2, and that gives me x squared equals minus 2 log 1 minus u. And then I take the square root and I get x equals the square root of minus 2 log 1 minus u. Now there's a little bit of a trick which is not needed, but 1 minus u and u have exactly the same distribution. Because uniform 0, 1, you take 1 minus and you get the same distribution. So instead of 1 minus u, I can use u. This makes a simpler formula. Otherwise, if I use 1 minus u, there's no problem. That also works perfectly well. So basically what we have as a result is that if I take square root of minus 2 natural log of u, then this has a chi-square distribution with 2 degrees of freedom. So if I take rand and I apply minus 2 ln rand and I take the square root, I will get a chi-squared distribution with 2 degrees of freedom.
Some condition है first third term और second term के दरमियान first line.
क्या हो condition?
वो माइनस एक्सपोनेंशियल 1/2 r square आगे वो जो
Oh, acha, that bar, that is actually the evaluation at the two limits. So there should be x equals 0 at the bottom and x equals 1 at the top. X equals 0, yani r equals 0 and r equals x at the top. Yeah. So this is the result that if the r is the square root of minus 2 log u, r squared is minus 2 log u. Remember, the r is the distance, r squared is the equal to x squared. Yeah. I think this is correct. Yeah. Right, this is actually the square root of a chi-square, if I remember correctly.
Sum of x squares?
Yeah. And this formula is correct, but r squared is equal to x squared plus y squared. So this r is not actually... No, this always has to be positive. So if you generate r as square root of minus 2 log u and theta as 2 pi v, where u and v are standard uniforms, then theta will be a uniform variable between 0 and 2 pi, so it will be the angle, which is equally likely to be any possibility, and r will be your square root of a chi-square, and so you will have set x equal to r cosine theta and y equals r sine theta, and you have your bivariate normal. This bivariate normal will be mean 0, variance 1 and correlation 0. This will be the standard bivariate normal. And now once you have these, then you can generate any bivariate normal using the tricks that we have already discussed. So this shows you how to generate bivariate normals in Excel, without using norm S inverse. Norm S inverse is powerful, and you don't need this trick. In the olden times when we didn't have access to such functions in Excel, then we needed to do these kinds of tricks to get normals. But anyway, still this trick is no longer very useful because now we have the norm S inverse, but it is useful in understanding the structure of the normal, so I explained it. Contents of this lecture and the previous lecture would be enough to teach a course in normal distribution theory, but I have been focusing on the engineering. The engineering aspects are very small, very trivial. Those are basically, in the previous lecture it was the standard normal and its properties, especially the central limit theorem. And in this lecture we talked about how you generate bivariate normal, what does correlation mean, the relation between and some properties of covariance, and basically how to construct. So basically the bricklayers version of these two lectures is that if you take a lot of random variables and add them together, you get normals, and normals have very nice properties. And if you take two independent normals, how you can get the joint density, from the joint density, how you get the conditional density and the marginal densities. Now these are the crucial elements of what we need to do the Bayesian analysis for the normal. So I think we have had a lot of theory, so next time I was planning to do multivariate, but that will be really I think too difficult. So what we will do is Bayesian theory, so it will be real applied analysis next time for how you do the Bayesian analysis of a standard univariate linear regression model. So we know already how to estimate y equals alpha plus beta x plus epsilon in the classical method, and now we have all the theory we need to show how this is done in the Bayesian methodology, and so next time we will start on that.